Have you ever found yourself standing on the beach, you know, watching the waves,
Hmm.
and then slowly you start noticing something changes?
Yeah, the water line moves
Right.
a lot sometimes.
Exactly. The water that was like right at your feet is suddenly way out there showing all this sand.
Or it's creeping higher, maybe reaching the towels.
Right. It happens every day, this rhythm. But have you ever really stopped and wondered why? Why does the sea rise and fall like that so consistently?
It's such a fundamental thing for our planet, isn't it? We see it all the time, especially if you live near the coast. But the actual mechanics, the power behind it,
Yeah.
it's often just taken for granted.
Totally. And this, well, seemingly simple process is what we call tides.
That's the one.
And for this deep dive, we're going to really unpack the unseen forces driving this ancient rhythm of the ocean.
It's so much more than just water sloshing around.
Oh yeah, it's this whole cosmic dance, really. Something that shapes human exploration, how we navigate, even the look of our coastlines.
Absolutely. And it all ties back fundamentally to Earth's partner up there in the sky,
The moon.
the moon. Its influence is just undeniable, even from so far away. It's a really fascinating story of these invisible forces having very, very visible effects.
Okay, so let's get into it. This cosmic dance. At the most basic level, what exactly are tides?
Well, put simply, tides are just the regular rise and fall of sea levels.
The pulse of the ocean.
That's a good way to put it. Yeah, the ocean's pulse felt most obviously along the coasts.
And for most people, I think the pattern they know is 2 high tides and 2 low tides each day. That's the common one.
That's the most common, yes.
Okay.
It's called the semi-diurnal pattern. Semi-diurnal meaning twice a day.
Got it. That rhythm dictates so much coastal life.
It really does.
Yeah.
But it's worth remembering, it's not the only pattern. Tidal patterns aren't actually uniform everywhere.
No.
Yeah, depending on where you are, the shape of the coastline, the ocean basin, some places might only get 1 high and 1 low tide a day. That's called diurnal.
1 cycle a day.
Exactly. Or sometimes the pattern is more mixed and irregular. Local geography plays a huge role in how those big global forces actually manifest on a specific shoreline.
Okay, so we know what they are, the rise and fall.
Hmm.
But the big question is why?
Right.
And this is where it gets, well, pretty amazing. We mentioned the moon.
The moon is the star player here. Its gravitational pull on Earth is the primary driver of tides,
Pulling on the oceans.
pulling on all that water. Its gravity is strong enough to literally pull the ocean water towards it.
Okay.
So on the side of Earth that's facing the moon right now,
Yeah.
the water there gets pulled, creating a bulge.
And that bulge is high tide.
That's your high tide. Makes intuitive sense, right?
Hmm.
Moon pulls water, water piles up.
Yeah, that part feels straightforward. Moon's right there, tugging away. But here's the bit that always messes with my head a little.
Okay.
You get another high tide on the opposite side of the Earth, the side facing away from the moon. How does that work?
Yes, that's the classic question, and it's crucial. It feels counterintuitive. So that second bulge, the high tide on the far side, isn't because the moon is somehow pulling water away from the Earth over there.
Right, that wouldn't make sense.
No. Instead, it comes down to the interplay between gravity and something called centrifugal force, or maybe more accurately, inertia. Think about the Earth and moon orbiting each other. They actually orbit a common center of mass.
Okay, like a balancing point.
Sort of, yeah. And as they swing around this point, the water on the far side of Earth is, well, further away from the moon than the solid Earth itself is.
Right.
So it experiences a weaker gravitational pull from the moon compared to the Earth beneath it. At the same time, because the whole system is rotating, there's inertia, the water wants to keep moving in a straight line. The combination means the water on the far side effectively gets left behind or flung outwards relative to the center of the Earth, creating that second bulge.
Ah, okay, so it's like a double act.
Yeah.
The moon's direct pull makes one bulge on the near
Yeah.
side, and then this inertia, this centrifugal effect, creates another bulge on the far side because the water there isn't pulled as strongly towards the moon as the Earth itself is.
You've got it. That's the essence of it. 2 bulges.
And because the Earth spins on its axis once a day,
Right. We rotate through these 2 bulges.
giving us 2 high tides,
Yeah.
and naturally, the areas between the bulges experience low tides.
Exactly. So when people say the moon causes the tides, they're essentially right. It's the main influence, even if the physics involves those 2 distinct effects.
Fascinating. But you said the moon is the main act. Does that mean there's more to it?
Well, yes. The moon is definitely the headliner, but it's not a solo performance. The sun gets involved too.
Ah, the sun's gravity.
Exactly. Now, the sun is obviously much, much bigger than the moon, but it's also vastly further away.
Right, so its pull isn't as strong here.
Its tidal effect isn't as strong, correct. The moon's proximity makes its gravitational influence on the tides about twice as powerful as the sun's, roughly speaking. But the sun's contribution is still significant.
Okay, so how does the sun play its part? Does it change things?
It absolutely does. It explains why tides aren't always the same height. Think about when the Earth, moon, and sun are all lined up.
Like during a new moon or a full moon?
Precisely. In that alignment, the sun's gravity and the moon's gravity are pulling in the same direction or opposite directions along the same line. They essentially team up.
Reinforcing each other.
Right. And the result is higher high tides and lower low tides. These extra strong tides are called spring tides.
Spring tides, got it. Not named after the season then.
No, confusingly. It comes from the idea of springing forth or being energetic.
Okay, so what about the opposite? When the tides are less extreme?
That happens when the sun and moon are at right angles to each other relative to the Earth. Think first quarter or third quarter moon phases.
So they're pulling in different directions, kind of perpendicular.
Exactly. In that configuration, their gravitational forces are working against each other, partially canceling each other out.
Oh.
This leads to weaker tides overall. The high tides aren't quite as high, and the low tides aren't quite as low. These are called neap tides.
Neap tides. So spring tides are the extremes, neap tides are the moderates.
That's a good way to remember it. And this constant interplay between the sun and moon explains that variability you see at the beach. One week, the tide might rush way up the shore. The next, it seems much gentler. It all depends on that celestial alignment.
It really is a dance. Okay, so we've got the forces, the sun and moon. What about the timing? You mentioned the semi-diurnal pattern, 2 highs, 2 lows a day. But if you actually use a tide chart, you notice something else. High tide isn't at the exact same time every day.
That's a very keen observation. You're right.
A full tidal cycle, say from one high tide to the very next high tide, isn't exactly 12 hours.
No, it's a bit longer. It's about 12 hours and 25 minutes on average.
Okay, 12 hours and 25 minutes. Why the extra 25 minutes? Where does that come from?
That extra time is another fascinating consequence of the moon's movement.
Ah, the moon isn't stationary.
Exactly. While the Earth is rotating on its axis, the moon is also orbiting around the Earth in the same direction.
Okay.
So think about it. Earth completes one full rotation in about 24 hours. But during that 24 hours, the moon has moved forward in its orbit.
Right, it's not in the same place in the sky relative to a point on Earth.
Precisely. So for a specific spot on Earth to rotate around and be directly under the moon again to line up for the next direct high tide bulge, the Earth has to rotate a little bit extra to catch up to where the moon has moved.
Ah, how much extra?
It takes about an extra 50 minutes of Earth rotation each day to catch up to the moon's new position.
15 minutes.
And since there are roughly 2 high tides per day, that extra 50 minutes gets split between them. 50 divided by 2 is
25 minutes. So that's the extra 25 minutes for each 12-hour cycle.
That's exactly it. The Earth is constantly playing this little game of catch up with the moon.
So just to make it practical,
Yeah.
if high tide today is bang on 6 a.m., tomorrow morning's high tide won't be at 6 a.m. It'll be closer to 6:50 a.m.
Roughly, yes. That daily shift is predictable and crucial for anyone who relies on the tides.
And that brings us to the real-world impacts, doesn't it? This isn't just abstract physics. It affects people's lives profoundly.
Absolutely. Think about navigation, especially historically.
Ancient sailors.
Ancient sailors, yes, but even much later. Before sophisticated charting and engines, knowing the tides was absolutely critical for safely entering harbors, navigating river estuaries, or avoiding hidden sandbanks revealed only at low tide.
Getting it wrong could mean disaster.
Literally life or death. And even today, fishermen plan their entire schedules around tidal charts.
Why is that?
Well, fish behavior is often strongly linked to tides. Strong tidal currents can stir up nutrients from the seabed, attracting smaller organisms, which in turn attract the larger fish fishermen are after.
Ah, so the tide brings the buffet.
In a way, yes. Certain times in the tidal cycle are just much more productive for fishing. Knowing the tides means knowing where and when the fish are likely to be active.
And beyond human activity, the environment itself.
Oh, fundamentally shaped by tides. Coastal ecosystems like salt marshes, mangrove forests, tidal flats. These are unique environments that exist because of the regular ebb and flow.
They depend on that cycle of being submerged and exposed.
Completely. Tides transport nutrients, sediments, flush out waste, create habitats for specialized plants and animals.
Hmm.
They're the lifeblood of these coastal zones, driving incredible biodiversity.
It's amazing how far-reaching it is. You even mentioned historical events earlier.
Yes, there's a really striking example, the Allied D-Day landings in World War II.
Really? Tides played a role there.
A massive role. The timing of the entire operation, landing thousands of troops and vehicles on the Normandy beaches, was meticulously planned around the tides in the English Channel.
How so?
Well, they needed a low tide that was rising. Low tide would expose the German beach obstacles mines, barriers allowing Allied engineers to clear paths.
Ah.
But they needed the tide to be rising, so the landing craft could get further up the beach as the invasion progressed, depositing troops closer to cover and reducing the distance they had to cross under fire.
Wow.
They also needed specific conditions regarding the full moon for visibility for airborne troops landing the night before. Getting the tides and the moonlight right was absolutely critical to the plan's success.
That's incredible. A pivotal moment in history hinging on the gravitational pull of the moon and sun.
It truly shows how understanding and predicting these natural forces can have monumental consequences.
Absolutely. And the story of tides, it seems, gets even more profound when you look deeper. Some really mind-bending implications.
There are some fascinating aspects, yes. For example, have you ever stopped to think, what if we didn't have the moon?
No moon at all. Wow. Well, the nights would be darker.
Definitely darker.
Yeah.
But thinking about tides, what would happen?
Well, based on what we said, the moon is the main driver. So tides would be much weaker.
Much, much weaker. They wouldn't vanish entirely because the sun still has its gravitational effect. We'd still have solar tides, but they'd be significantly smaller, less than half the strength of the tides we experience now. The dramatic daily swings would be largely gone.
That would change coastlines drastically.
Hugely. And the moon does more than just cause strong tides. It also acts like a stabilizer for Earth's axial tilt, the angle our planet spins at.
Which gives us our seasons.
Exactly. Without the moon's steadying influence, Earth's tilt could wobble much more chaotically over long timescales, potentially leading to extreme climate shifts that might make it harder for complex life to thrive.
So the moon is kind of our climate stabilizer, too.
In a very real sense, yes. Here's another mind bender for you.
Okay, I'm ready.
Tides are actually slowing down the Earth's rotation.
Wait, what?
How? It's due to something called tidal friction. Think of those huge bulges of water being dragged across the Earth's surface as it spins. That water movement creates friction against the ocean floor, especially in shallow seas. It acts like a very gentle brake.
A break on the whole planet's spin.
A tiny, tiny brake, yes. The effect each year is minuscule. It lengthens the day by a fraction of a millisecond.
Okay, so I won't notice it by tomorrow.
Not by tomorrow, but accumulate that effect over millions, hundreds of millions of years.
The days get longer.
The days get noticeably longer. Billions of years ago, Earth's day was much shorter. Tides, driven primarily by the moon, have been gradually slowing us down ever since.
That's incredible. Our sense of time itself is being shaped by this gravitational interaction.
It's a profound connection, and scientists study tides for more than just oceanography or navigation.
Like what?
Well, the slight flexing of the Earth's crust caused by tidal forces. Yes, even the solid Earth has tides, though much smaller can give clues about the planet's interior structure. And tracking long-term changes in sea level, combined with tidal data, is crucial for understanding things like land subsidence or uplift, and of course for monitoring the impacts of climate change and sea level rise. Tides are a key vital sign for the planet.
So, wrapping this up, we started with just watching the water move on a beach. And it turns out tides are so much more than that. They're this intricate result of a cosmic dance.
A gravitational ballet, really, between the Earth, the moon, and the sun, playing out constantly.
And this dance, this delicate balance, affects everything from tiny marine organisms to global climate, from ancient navigation to modern science, even the length of our day.
It's a constant, powerful reminder of the unseen forces that shape our world and our deep connection to the cosmos. The moon isn't just a pretty light in the sky, it's actively shaping our planet every single moment.
So the next time you're by the coast, take a moment, watch the tide come in or go out.
Yeah.
And maybe think about that quiet partner overhead the moon, pulling the strings of this vast ocean rhythm.
It gives you a different perspective.
Definitely. And maybe leave you with this thought to ponder. What do you think would happen to life on Earth, as we know it, if we didn't have the moon?
It's a deep question. Really puts the importance of tides and our moon into focus.